Hi, this is the third video in data structure and algorithms. In the last video, we talked about stack, queue, priority queue, and dequeue. In this video, we will talk about list, unordered set, and sorted set. Let's start talking about the list. The list is a general data structure. It has many operations like add element x in the index I, or remove the element in the index I, or set the element index I to be x, change the value of the element in index I to be x, or get the value of the element in the index I, get I. So the list is, we said it's general data structure because using the list you can make a stack or queue or even dequeue. So the list will look like this. We have elements. Every element have index. It's like an array. Okay, it's similar to array. The index has 0, 1, 2, 3, 4, 5, 6, 7 to n minus 1. And every element has a data. Okay, let's say a character. So this list represent a collection of elements and they have indices. So if I call get2, then I will get the element in the index 2, which is C. So the list operation, the first operation is size. I will know it will return n, the length of the list. How many elements do I have in the list? The operation get I return the value of xi, the value of the element in the index I. And set ix, it set the value, change the value in the index I to be x. If I make add ix, then I will add new element. I will make it in position I, and I will just shift all the elements after this element to the right. Okay. If I remove I, then it will remove xi. It will remove the data in position I, and it will shift left all the elements after this element. So let's us take some code example. The list in Java, we have a class called linked list. In the package java.util, we can create an object of this linked list. Let us add Jana to position 0, and then add Fatma to the position 1, and then add Haifa to the position 1. When I add Haifa to the position 1, it will be in position 1, and Fatma, which was previously in position 1, will move to position 2. So if I print here the list until line 26, I will get Jana, Haifa, which was added in the place of Fatma, and Fatma was shifted right, and then Fatma. Okay, if I want to get 2, then I will get Fatma because Fatma is the name in position 2. If I want to remove 0, it will remove the first element in the list. So it will remove Jana and will shift Haifa and Fatma to the left. So Haifa was previously in position 1, it will be in position 0. Same like Fatma was in position 2, it will be in position 1. If I print the list after this, I will see Haifa and Fatma. If I set the value of 1 to be Noura, this will change the value of element in index 1 to be Noura. So it will be Haifa and Noura. I can easily make a dequeue out of list. How? So you remember in the dequeue we have first important operation, add first, remove first, add last, and remove last. But in the list, add first is just add to the position of 0 the value x, right? And remove first is just remove the element at index 0. Add last, it will add a new element after in the index after the last index, which is size or n. Okay, so in this case I will add in the position of size. Let's say we have previously a list of 8 elements. Okay, so the indices will be from 0 to 7. It has 8 elements. I want to add a new element. I will add it in position 8, which is the size of the previous list. So add size x. If I want to remove the last element, let's say you have now a list of 8 elements from 0 to 7, and you want to remove the last, so you will remove 8 minus 1. You remove the element from position 8 minus 1, size minus 1. So with this I can get a DQ out of the list. Also I can get stack using only the first 2 operations, right? Or I can use the first operation and the last operation to get a Q. So we know how to make a DQ, to make a stack out of DQ or a Q out of DQ. So this tells you that linked list can give us all the data structures that we learned so far. Let's move to a new data structure called unordered set. So unordered set means it's unordered. There is no ordering between the elements. And because it's set, it's unique. There should be no repetition in this set. It's similar to the mathematical set. The operation for the unordered set operation, the size, it will just return the size of the elements in the set. We can add new elements, but make sure that this element does not exist. If this element exists in the list, we are not allowed to add it. Then we will get a false. But if this element is a new element and we want to add it in the list, we will get true. Okay, and add this element in the list. Remember, there is no ordering, so it doesn't matter where we add it. Okay, and then there is an operation called remove. It will remove x. It will search for x in the list and remove it. If this x exists, then it will return x and remove it. If it does not exist and we want to remove x which does not exist in the list, we will return null. And we cannot remove it because it does not exist in the list. Find x, it will return the element that contain x. Okay, find an element y in the set such that y equal to x. If x does not exist in the set, we will return just null. So this was the unordered set. We have another data structure called the sorted set. So the sorted, from the name, it's sorted based on some order. And again, there is no repetition because it's set and it's similar to the mathematical set. So we said there is an order. So this means you can compare two elements. You can compare x and y. Maybe they are equal, or x greater than 0, or x less than y. Okay, so if x is less than y, I return a number which is less than 0. If it's x is greater than y, I return a number which is greater than 0. If they are the same, I return just 0. So this means there should be a method that compare two elements in the set, right? Because I want to know which one is bigger. Okay, for number it's easy, because if I have two numbers, I can easily make order of them. But what if you have strings? If you have strings, then maybe you can order them based on the alphabetical order or lexicographical order. What if you have like photos? How you want to order them? I can order them, let's say, based on the image size, right? So you should, in the sorted set, you should have some order between the elements. The operation in the sorted set is very similar to the operation in the unordered set. So we have a size, return the number of elements in the set. We have add x. We'll try to add new element. If this element exists, then the addition will happens and we return true. If this element already exists, then we cannot add it. and it will return false. Remove x. If this element already exists, we will get the element, it will be removed and we will get it, we will return it. If there is no x in the set and we want to remove x, we will just get null and no removal will happen. Find here is a little bit different than the previous find in the unordered set. Find here, if you want to find an element, you go over the order. You start from the beginning and you try to find the first element which is greater or equal x. So you return y. So y is not equal to x. It could be like the closest element greater than x, okay? But I return y. If there is no element greater than x, there is no x and there is no element greater than x, then I return null. Okay, something in data structure and algorithm we deal with is asymptotic notation. Why we have asymptotic notation? In the future, in this course, we will be comparing algorithms or the implementation of operations. We want to see how to search in an array, okay? You have one method to search, there is another method that search in a different way. We want to compare which one is better, which one is faster, okay? One way is just to run the two methods and see how many milliseconds does it take, the first method and the second method. But this is not a good solution. Why? Because the exact running times varies from computer to computer. You can go to a fast computer and run the algorithm, it takes 2 seconds. You go to a slow computer, it takes 5 seconds. So you cannot really compare between algorithm by saying this algorithm takes 2 seconds, because this depends on the computer, this depends on how fast the processor is, you know. So this is not a good solution to tell me that this algorithm takes this time. Another solution is to count the number of operations. You just tell me that this algorithm needs 100 operations, while this algorithm needs 200 operations. So the first one is better. It only takes 100 operations. Second, 200 operations. So this method is better than counting the time, because you count how many work you need to do in this algorithm and this algorithm. The problem, it's really difficult to count exactly how many operations. So the second solution is the asymptotic notation. In the asymptotic notation, we don't really count the exact number of operations, but we can give you a rough idea about the number of operations. So let us give a concrete example. We have algorithm. Okay, this algorithm, what the algorithm do? It's an we have array A, and we go through all the array and fill it with the value I. So the first element will in the array, it will be 0. The second element we will fill it with 1. Third element 2, 4, 5, unless we come to the end of the array, n minus 1. The last element will have a value of n minus 1. So we create an array and we store in the array just the indices stored in the elements. Okay, we need to know this algorithm or this code or this operation, how good or bad is it. Okay, so we want to count the number of operations. First, in the for loop, this statement int I equal to 0, it will be executed 1, right? And then this comparison will be executed n plus 1 time. Why? Because I make comparison the first time when I equal to 0, 1, 2, 3, 4, n minus 1, and also the last comparison when I equal to n, then this becomes false. So I do n plus 1 comparisons, okay? So, and then increments, I do n increments. And here this line is executed n times because it's inside the loop. Okay, I have n array offset calculation, and this is like one operation, and the assignment is another operation. Okay, so I'm trying to count how much operation this for loop needs, right? So we could write the running time as the following. We say it's A. Let's say A is the time I need to do the assignment. I need B multiplied by n plus 1. Let's see, B is the time I need for comparison. And then C is the time I need for increment multiplied by n plus D multiplied by n plus E multiplied by n. But this is very complicated, right? It's complicated form. It doesn't give me like insight, or it's not easy to calculate and to count every operation here. So in the asymptotic notation, we will just need to know how good is this algorithm, T of n, that running time of the algorithm. So we come up with the notation, it's called big O notation. This notation can simplify things. I just tell you, if the number of operation in n is roughly n, is not more than n, roughly, okay, approximately speaking. So with this, I know if I have an array of 1000 element, I know I just approximately I need 1000 operation, or 2000. So it's in the thousands area. Yeah, it's not 1 million, it's 1 billion. It's relative to the number of the elements in the array. If you have an array of 1 million elements, then you need some operations related to the number of elements in the array, to the 1 million. So it could be 3 millions, 4 million, half million. So it's in the million range, but it will not be billion or trillion operations. Okay, so this is the asymptotic notation. Help me to simplify things. So the formal definition of the big O notation, if I say this function or this algorithm is big O of n, this means all the functions that are roughly close to n or even smaller than n. Okay, so when I say this algorithm is big O of n, this means that this algorithm is not bigger than n approximately. Okay, we here in the big O notation we ignore constants, and we ignore like the beginning of the function. So let's see the formal definition. So the big O of a function f of n is all the function g of n that are less than or equal f of n multiplied by some constant and after some initial condition. Okay, so this means any function that is less than f of n, it should be big O of f of n. We will take examples about this, and with the analysis of in the rest of the book, we will talk more about the big O notation, and we will see how we compute the big O notation. We just want to give you what's definition of what is a big O notation. So for example, imagine you have algorithm, you try to count the operation. The operation you need is 5n multiplied by log n plus 8n minus 20. So this is for sure is less than 5n log n plus 8. So we remove the 200 because it's minus. Okay, and then this is less than or equal 5n log n plus 8n log n. So I make this term bigger, so this will make this complete thing is bigger than these things. Okay, I have this. So 5 plus 8, it's 13n log n. Okay, but I don't care about constant. In the big O notation, you don't care about constants. If you have constant, just delete it. And then with this, I know that this complicated thing, I can just say this is big O of n log n. I just simplify things. And this happens by choosing c equal 13. So I ignore multiplication by 13, but it doesn't matter because I just want to know roughly how how many operations. I don't need the exact number of operations, okay? So when we talk about algorithms, we care about two things: the time complexity, the running time of the operation, how many operations you need to do to compute this or to do this, right? This is called time complexity. There is another factor, it's called space complexity. Space complexity means do you need to use a lot of memory, or you want to use no memory in the operation, or you want to use many memory, you know? You just tell me how much space you need to perform this operation, and we will see examples, a lot of examples in this course. So today's lecture, if you didn't really understand what's big O notation and what's time complexity, space complexity, we will be repeating this in all coming operation and function and algorithms. So let us take exercise. The first exercise, we have a string of a sequence of brackets and parentheses, you know. Let's say you have this sequence, this open bracket, close bracket, open bracket, close, open, close, okay? So we have a sequence of these characters that are probably matched. For example, if I have these characters is a match, we call it a match string. Why? Every open has a closed, right? Every open have a closed, and it's in the same order. So imagine you encounter this in a code, then this is correct bracketing, right? But for example, this is not correct. Why? Because this open bracket is not closed. Okay, there is one close here, but the other one there is no closing one for it, and also this bracket is not opened before. So this is not, because this is not matched with this, okay? So show how to use a stack. We want to use a stack so that given a string of length n, you can determine if this is a matching string, and we need to do this in big O of n times. So you need to do this in roughly n operations, or let's say 2n or 10n operation. It's all of these are considered big O of n, right? We ignore the constants. So this is the first exercise. The second exercise, suppose you have a stack S, and this stack is full with elements. The stack has push X and pop, as we know. Show how using FIFO queue, we want to use a queue. So we want to reverse the order that the element in the stack is. So imagine you have stack, it has like 4 elements, Ahmad, Mahmoud, Khalid, Sumaya. And then I want to use a queue so that I can reverse the elements in the array. So try to think about this exercise, and see you in the next video.